Hey everyone, and welcome back. Today we're going to be continuing our journey through differential equations and talk about something called systems of differential equations and how they relate to higher order differential equations, for which we've been spending most of the recent time looking at different ways of solving higher order differential equations. So first off, we need to answer what exactly is a system of differential equations and what's their relationship to higher orders. So as a guiding example, let's just look at a second order differential equation, because if you can do it for second order, you can do it for any order higher than that. So the general second order differential equation can be written as y double prime plus a1 of y prime plus a0 of y is equal to 0. And we can assume without loss of generality that a1 and a0 are not necessarily constants, but functions of x. So notice here that the order for this particular differential equation is equal to 2. So this number 2 is going to play a very important role in the translation of higher order differential equations to systems. So what we want to do is we want to introduce two new variables. In particular, we're going to introduce variable eta1 and variable eta2. So eta1 is going to be defined to be equal to y, and eta2 is going to be defined to be y prime. So if we take the derivative of eta1 with respect to x, because keep in mind y is a function of x, so therefore eta1 must also be a function of x, therefore eta1 prime will be equal to y prime, and eta2 prime will be equal to y double prime. Keep in mind, y prime has a new name, its name is eta2, therefore we can just write eta1 prime as just eta2, and y double prime has a new name. It's in terms of the original differential equation, because keep in mind we can isolate y double prime in a second order differential equation, and instead write that as minus a0y minus a1y prime, and that's just going to be equal to what? Well, y is just equal to eta1, and y prime is just equal to eta2, right? So we have that eta1 prime equals eta2, and eta2 prime is equal to minus a0 eta1 minus a1 eta2. So if we write that in vector form, so we can say eta1 eta2 prime is equal to, so in the first equation notice that there's no eta1, so it's going to be 0 times 1 times eta1 eta2, and in the second equation notice we have minus a0 there, and we have minus a1 there. Right? So notice that we have a matrix equation here, and we can write this in vector format. For example, we can call eta1, eta2 the vector, just as the vector eta. We can call this matrix A, which could be a function of x, and here we have eta again. Right? So we have eta prime is equal to ax eta. Right? So if we write that, we have eta prime. So eta prime is equal to ax eta, right? And if we write that in differential form, that's the same thing as d eta x is equal to ax eta, which is a separable differential equation. But keep in mind, eta is not a variable in this case. Eta is a vector. So it's a separable vector ordinary differential equation, right? So keep in mind, it's not just a separable vector ordinary differential equation, but it's a separable first order ordinary differential equation, because there's only one derivative hanging out here, and that's d eta dx. Okay, so we already know how to solve these types of differential equations because they're just first order, and just because they're vectors, that just means that our solutions are vectorized as well. Right? So if that's the case, that means theoretically we can solve any higher order differential equation by first translating it into a first order system of differential equations and then solving that separable vector first order differential equation as a result. Right? So you may be thinking like, okay, well that's pretty cool, but does it offer anything new that we didn't originally have? And the answer is of course yes, and that comes with numerical methods. So if we look at numerical methods for first order differential equations, We have quite a few. For example, we have Euler, Taylor series methods, RK2, RK4, RK3, and any variations thereof, right? So if we look at this particular differential equation, in particular y double prime plus a1y prime plus a0y is equal to 0, we already have discussed that we can write this in eta 1 prime of x is equal to eta 2 of x, and eta 2 prime of x is equal to minus a0 eta 1 of x, and then minus a1 eta 2 of x. So if we want to solve this differential equation, say with an Euler's method, so if we use an Euler approach, or RK1 approach, I guess you could say, then if we just do a forward difference approximation, that's just going to give us what? So that means that eta 1, so eta 1 of x plus h will be equal to eta 1 of x plus h times that right-hand side of that differential equation, which is just going to be equal to eta 2 of x. And eta 2 of x plus h will be equal to eta 2 of x plus h times the right-hand side of that equation, which is just going to be minus a0 eta 1 of x minus eta 1 eta 2 of x. Agreed? So keep in mind that this is our differential equation, and in system form at least, and this is our original second order differential equation. So we typically are going to be giving two initial conditions: y of x0 is equal to y0, and y prime of x0 is equal to y10 or something along those lines, right? I guess we could call it y prime of 0 just to keep things simple, right? So those are both numbers. Agreed? So once you have that, then you can be like, okay, well, how would I use this in a forward difference manner? Well, that means that, for example, eta 1 of x0 plus h will be equal to eta 1 of x0 plus h of eta 2 of x0, and eta 2 of x0 plus h will be equal to eta 2 of x0 plus h minus a0. Let's assume that's a constant just for simplicity. Eta 1 x0 minus a1 eta x of 0, and that should be, of course, eta 2. And you're going to be like, well, do I really know what eta 1 x0 is and eta 2 x0 is? The answer is actually yes, because keep in mind, eta 1 of x is the same thing as y of x, and eta 2 of x is the same thing as y prime of x. So from these definitions, that means that eta 1 of x0 is the same thing as x0, which we define to be equal to y0, and eta 2 x0 is the same thing as y prime of x0, which we define as y prime of 0, which we do know, right? So these points are just in the past, and this is an approximation for y, and this is an approximation for y prime, where probably the main focus of solving the differential equation is y, right? But keep in mind, we do need to update eta 2 because eta 2 is used in the definition of eta 1, right? But in the end, when you're solving the second order differential equation, your goal is to capture this eta 1 with as much accuracy as possible. Let's work through an actual example to sort of see how this will work on the MATLAB side. Let's assume that somebody gives you this second order differential equation, which you probably will already recognize this as the Legendre differential equation, right? Because we have our 1 minus y squared, we have the derivative of 1 minus y squared in the front of y prime, and this 20 is just a fancy way of saying 4 times 4 plus 1, which is 4 times 5, which is 20, right? So that means the solution to this differential equation, y, is just a Legendre function of order 4. Right, so it's the fourth order Legendre polynomial, I guess you could say, right? And here we have some initial conditions to well define that particular definition. So if you don't know how to solve this, and probably power series would be one of the more nicer ways of representing the exact solution, you'd probably go to a numerical method to try and solve it. So let's just go ahead and do an Euler approximation for just a little couple time steps. Let's say we're at x0 is equal to 0. Let's just do a time step of 0.1 and then go to like 0.1 and 0.2 for the approximations, okay? So since we have a second order differential equation, the first thing that we want to write is this differential equation as a first order system. So we need to start off by defining eta 1 to be equal to y and eta 2 being equal to y prime. So that means that eta 1 prime will be equal to y prime, which we know is going to be eta 2, and then eta 2 prime. So eta 2 prime is just going to be the same as y double prime, and then we need to just solve that differential equation for y double prime, which is going to be positive 2xy prime minus 20y all over 1 minus x squared, right? And once we write that in terms of eta 1 and eta 2, that's just going to be equal to 2x eta 2 minus 20 eta 1 all over 1 minus x squared, okay? So that's eta 2 prime, and then here's our eta 1 prime. So once we have that defined, now we can use our first order approximation with the Euler's method. So that means y of x plus h will be approximately equal to y of x plus h y prime of x, and then y prime of x plus h, which keep in mind is just eta 1 and eta 2 in disguise, is going to be approximately equal to y prime of x plus h, and then this little thing, right, which is just going to be 2x y prime of x minus 20 y of x all over 1 minus x squared. All right, so once we have our system set up, now we can go ahead and solve it. So if we let h be equal to 0.1, arbitrarily large, but if you're in a computer you can make it small if you want, and using our initial condition that y of 0 was chosen to be 3/8 and y prime of 0 was chosen to be 0, that means that y of 0.1 will be given approximately by y of 0, which we know is 3/8, plus h, which is chosen to be 0.1, and then times y prime of 0, which was chosen to be 0. So this is actually trivially 3/8. And then y prime of 0.1 will be approximately equal to y prime of 0, which was chosen to be 0, plus h times 2, x is 0, and then we have y prime of 0, minus 20 times y of 0, which is 3/8, all over 1 minus 0 squared, which you can find to be equal to negative 3/4. Now keep in mind, if you're just trying to approximate y at 0.1, you technically don't need the next statement. The next statement is just going to be used to find the approximation of y 0.2 using y prime of 0.1 in that particular step, right? So technically you can save that last line of calculations if you do not need the next step that follows after. Right, but we do. Let's assume that we want to go through y of 0.2, so what will that be? So y of 0.2 will be approximately equal to y of 0.1, which we found to be 3/8, plus our h times y prime of 0.1, its approximation, which was given to be approximately negative 3/4, and then we have y prime of 0.2 to be approximately equal to y prime of 0.1 plus h times 2, 0.1, our approximation for y prime 0.1, minus 20 times y of 0.1, all over 1 minus 0.1, the quantity squared, which you can find to be approximately equal to negative 1.5227. Okay, but keep in mind, if you only want to go up to y of 0.2, you do not need y prime of 0.2, but if you need y of 0.3, you're going to be needing that in that circled little step there in green. Right, but we have that at 0.1 and 0.2, our fourth Legendre function is approximately equal to 3/8, and also that's going to come out to 0.3 approximately. So you can do this for third order, fourth order, fifth order differential equations because it's practically the same exact setup, except it's just a couple more etas thrown at the end of your first order system implementation. Now that we see that first order systems can allow us to develop numerical methods for higher order differential equations, let's see if they can help us develop analytical solutions for higher order differential equations as well. To sort of help us guide on this little journey, let's consider a constant coefficient homogeneous differential equation to start. In particular, y double prime minus 5y prime plus 6y equals 0. So we know that if we have this particular setup, then obviously a natural solution would be e to the lambda x and a linear combination of independent forms of it, right? So if we let y be equal to e to the lambda x, then we're going to get the characteristic equation y squared minus 5 lambda plus 6 is equal to 0. So lambda squared minus 5 lambda plus 6 equals 0, which, as we already know, easily factors into lambda minus 3 times lambda minus 2 is equal to 0, which gives us two lambda values. In particular, lambda is equal to 3 and 2. So that gives us the general solution to this differential equation to be equal to c1 e to the 3x plus c2 e to the 2x. Okay. So we already know how to solve this type of differential equation, but maybe first order systems can help us sort of see the same exact solution, but from a different angle. So let's assume that we do not know how to solve this differential equation, and let's assume that we want to use first order systems to help us do it. So what we're going to do is we're going to let eta 1 be equal to y, and eta 2 be equal to y prime, as we have done already before. So that means this is going to give us eta 1 prime, which is equal to y1, y prime, which is equal to eta 2, and eta 2 prime, which is equal to y double prime, which if we isolate this particular equation is just going to be equal to 5y prime minus 6y, which is the same as minus 6 eta 1 plus 5 eta 2. So once we have this first order system set up, we can write it in matrix form very, very easily. In particular, we're going to have eta 1, eta 2 prime is equal to 0, 1, minus 6, 5, times eta 1, eta 2. So this is our first order system equivalent for our original second order differential equation. So clearly, we can write this as eta prime is equal to a eta, where this is our eta prime, this is our a, and this is our eta. And if we represent differential operators in operator form, this is just d eta is equal to a eta. Right? So notice that this is practically the same exact structure as eigenvalues and eigenvectors in linear algebra. In particular, we can say, is this really related to eigenvalues of a particular matrix? In this particular case, matrix is our D. And then that means that this eta vector represents eigenvectors, possibly in some sense, right? So solutions of differential equations can be viewed as eigenvectors, and the rate parameters, the lambdas, those would be the eigenvalues associated to our solutions, okay? So are they really connected in any way? Well, we can explore, because this is a numerical matrix A, so we should be able to find the eigenvalues and eigenvectors of that 2 by 2 numerical matrix just like we did before. So let's assume that we have this matrix A, which is equal to 0, 1, minus 6, 5, and let's assume that we want to find the eigenvalues of this particular numerical matrix. So in case you do not remember, in that particular case, all eigenvalues will satisfy this particular equation lambda, and x its associated eigenvector. Keep in mind, eigenvectors, there are infinitely many associated to a particular eigenvalue, but they're all going to be scalar multiples of each other. So in order to find the eigenvalues of a square matrix, the first thing that you need to find is the characteristic polynomial for that particular matrix, which is a function of lambda, and it's going to be found by doing the determinant of the matrix A minus lambda I, where I is the same exact dimensions as matrix A, and lambda is just some unknown value that we're going to find. So in this particular case, that's going to be equal to the determinant of the matrix 0 minus lambda, 1 minus 6, 5 minus lambda. That's a 2 by 2 matrix, so its determinant is actually quite simple. So that's going to be equal to minus lambda times 5 minus lambda minus 6 times minus positive 1, which is just going to be equal to lambda squared minus 5 lambda plus 6. And the eigenvalues are when the characteristic polynomial is set equal to 0, and this gives us the equation that we have. But you should notice that this is the same exact thing as the characteristic equation as we did when we were actually solving our constant coefficient differential equations. So we will still call this the characteristic equation for our matrix, just like this was the characteristic equation for our differential equation. right? So if that is the case, this still is factorable in the same exact structure. Therefore, we're going to have two eigenvalues, lambda 1, which is equal to 3, and lambda 2 is equal to 2, right? So those are our eigenvalues for our 2 by 2 numerical matrix. Now, what's not obvious is the eigenvectors of this particular matrix, okay? So if we substitute this, so a minus lambda I x is equal to 0, we need to find the vector x that is associated to this particular matrix equation for each of these lambda values, 3 and 2 respectively. So if we use the lambda value of 3, that's going to give us the equation minus 3, 1, minus 6, 2, x1, x2 is equal to 0, 0. And our goal is to find what x1 and x2 are. So if we reduce for echelon form this particular system, we're going to have 1 minus 1/3, 0, 0, times x1, x2 is equal to 0, 0. So we should be able to clearly see that the eigenvector, or a eigenvector for this particular matrix, for this particular eigenvalue of 3, is going to be equal to 1, 3. Right? Similarly, for this other eigenvalue, if we substitute 2 into this equation, a minus lambda I x is equal to 0, we're going to have minus 2, 1, minus 6, 3, times x1, x2 is equal to 0, 0. And if we reduce for echelon form that particular equation, we're going to have 1 minus 1/2, 0, 0. x1, x2 is equal to 0, 0. So you should be able to see that a eigenvector associated to eigenvalue of 2 is going to be equal to the vector 1, 2. Right? So once we have this, then what are we going to have? So if we use or look at this matrix differential equation, eta prime is equal to a eta, which is the same thing as eta prime minus a eta is equal to 0. If we start to treat eta as a variable, not really a matrix, then this is still a constant coefficient or constant coefficient matrix, first order differential equation with characteristic polynomial lambda minus a is equal to 0, which means that lambda will be equal to a. So if we use the same exact idea that we had before, that means eta of x, where eta is technically a vector in this case, is going to be equal to some constant times e to the ax, where a is that particular value, but in this case technically a matrix of coefficients as well. So we have this particular matrix equation. So using this flow of logic and the things that we had before, that means eta 1, eta 2 will be equal to some constant c1 times 1, 3 e to the 3x plus c2, 1, 2 e to the 2x, right? So this is our first eigenvector. That's our first eigenvalue. This is our second eigenvector, and this is the second eigenvalue. Technically, you can be grouping these eigenvectors together because they are technically scalar multiples of each other. And when we convert this back into our original solution form, that means y of x will be equal to c1 e to the 3x plus c2 e to the 2x, which is our typical solution. But we also get the solution for the derivative as well. In particular, y prime of x is equal to 3c1 e to the 3x plus 2c2 e to the 2x. So we get that from this eigenvector eigenvalue equation, but you should also be able to get that by just differentiating the first solution, and you get that same exact thing too. So, eigenvalues and eigenvectors for first order systems can actually help you get the same exact solutions without possibly analyzing things in the frequency domain, say with Laplace transforms, or using educated guessing like we did with, say, the inhomogeneous equations, or using some complex algebraic methods such as the method of variation of parameters. So we clearly see that first order systems definitely are hiding a lot of our information behind the scenes for higher order differential equations, And systems also allow us to numerically solve higher order differential equations without having to introduce any new fancy methods, right? But do first order systems actually have a world of their own? And the answer is, of course, yes. So let's assume that you have a particle that's moving in a two-dimensional plane. Let's assume R2, and it has an x and y value coordinate at any time t, let's assume greater than or equal to 0. Right? And let's assume, depending on where it is moving with respect to time, it sort of depends the direction depending on what time it is and the location that it's located at, right? So this point could represent t is equal to 0, this could represent t is equal to 1, t is equal to 2, and so on. And let's assume that this is the x, y plane. So, is it possible that we can solve this first order differential equation, first order system of differential equations, to find a closed form representation for the x and y coordinates in any particular time t, provided that we know how it is moving or how the x and y coordinates are changing with respect to time t? So keep in mind this notation here, for example, x prime of t is just a fancy way of saying dxdt, and y prime of t similar is going to be dy dt. All right. So the first thing that I want to do is I want to write this as a matrix equation. In particular, xy prime is equal to 4 minus 3, 6 minus 7 times vector xy. And I'm going to name this coefficient matrix a name. I'm going to call this A, and I'm going to start off by finding the eigenvalues and eigenvectors of this matrix and use the same exact notion and idea and motivation that we used in that last example, in particular for our second order differential equation, and sort of see if we can solve it in the same exact way. So let's start off by finding our little eigenvalues. So to find our eigenvalues, we need to find our characteristic polynomial, which is found by doing the determinant of a minus lambda I, which in this case is 4 minus lambda, minus 7 minus lambda, minus 3, and 6, and then we're going to be setting that equal to 0 in order to find our eigenvalues. So once we AD minus BC that for our 2 by 2 formula, that's just going to give us lambda squared plus 3 lambda minus 10 once you combine like terms. So once we have our characteristic polynomial, we're just going to set that equal to 0 and factor. So this actually factors quite nicely into lambda plus 5 times lambda minus 2 is equal to 0. So we're going to have two eigenvalues, the first of them being minus 5, and the second eigenvalue being positive 2. So once we have our eigenvalues, now we can move on to finding our eigenvectors. So eigenvectors. Alright, so let's start off with lambda 1. So for eigenvalue, lambda 1 is equal to minus 5. Our A minus lambda I matrix is going to turn into 9 minus 3, 6 minus 2, x1, x2 is equal to 0, 0. Keep in mind you're always going to have a free variable when you solve this particular type of equation because there are infinitely many eigenvectors associated to an eigenvalue. So when you reduce or echelon form that, you can find that the eigenvector for lambda 1 is equal to minus 5 can be represented as scalar multiples of the vector 1, 3, right? And keep in mind you can write that as 3, 9, 1/3, 1, or any scalar multiples of it. So that's not a unique representation. I'm just choosing the nicest integers, at least in my opinion. So for lambda 2 is equal to 2, we're going to have a minus lambda I come out to 2 minus 3, 6 minus 9, times x1, x2 is equal to 0, 0. And that's going to give us an eigenvector to be scalar multiples of the vector 3, 2. So once we have our eigenvalues and our associated eigenvectors, then we should be able to state our general solution for our first order system. So that means xy will be equal to c1, 1, 3 times e to the minus 5x, or in this case it's minus 5t. So let's just change our little variables around, so 5t, and then plus c2, 3, 2 e to the positive 2t. Right? So that's our vector representation for our solution to our first order system, and we can write this in expanded form as the following. In particular, x of t is equal to c1 e to the minus 5t plus 3c2e to the 2t, and y of t will be equal to 3c1 e to the minus 5t, and 2c2 to the positive 2t to be our solutions. And if I give you some initial conditions, for example, x0 is equal to x0 and y0 is equal to y0, in particular some initial conditions, you can find what this C1 and C2 are to sort of model the position of that particle throughout any time t for which you desire, right? But there are definitely plenty more theoretical and observational things for which we want to mention for first order systems, but this is just a little introduction to first order systems to sort of segue us from our discussion from higher order differential equations into systems and their properties. So until we get into those discussions for systems of differential equations, I hope you enjoyed this video and I hope to see you there. Take care.